Hello, my name is Dan Custer. Welcome back to our weekly training. Hopefully you got all your tests done from your pump training so that you can get a certificate and get that money. So we're going to move on to some different training now. We're going to call this portion of the training Jim Hudspeth's Neighborhood. So each week we'll have a different subject and we'll go over those things. So if you have any problems, something you'd like to discuss, you can just email us or text us and we'll get it on Jim Hudspeth's Neighborhood one of these weeks. So this week we're going to be talking about understanding speed and horsepower when changing pulleys. As normal, you can text any questions to 775-433-9390 or email questions to questions@reed-electric.com. And now we'll go to Jim.
Hi everybody, I'm Jim Hudspeth. Hey, listen, real quick, everybody needs a calculator. What I'm trying to get across to you is what can happen in the field, as well as understanding when you change RPMs from one speed to a different speed on electric motors versus changing pulleys and couplings. So right off the bat, I'm going to let Marvin describe a situation that happened at a cement plant that we were out at and give you an idea, a little bit about what we found, okay?
So we had our customer call us for a fan balance and our technician that went out there, we was having some difficulty on trying to balance it. The following day I went out to start the balance, found 16 loose bolts, several cracks on the frame. We started balancing it, leaned up against the motor. It was extremely hot for the short period of time that we were doing our runs. Called Jim, told Jim what was going on. He asked me a couple questions, gave him the answers to those questions, and found out that there was a different issue going on with the motor that was driving this fan. And I'll let Jim go over the calculations for you.
Okay, so one of the first things I want to do is just read this top page of the attachments that you guys should have in your hands. When changing speed with pulleys, when driving a fan or a pump, the horsepower required increases by the cube of the speed. So if we're driving a fan at 1775 RPM and it required 125 horsepower to do that, we would increase the fan speed to 2070 and would require a 200 horsepower motor. So it was 125 horsepower, and going the small difference between 1775 to 2070 now required a 200 horsepower motor to get it to operate properly. So when Marvin was just leaning on the motor, he immediately got off of it because it was so damn hot. He got concerned about that. So one of the first things I want to suggest is that when we go out in the field and do a field service job on a motor especially, go look at the motor if it's running, runnable, and see what the motor current is on it before you do anything. Then calculate whether that current is full current, or is it above the motor current, or where you're at with it. So some of the stuff that we're going to go over today is some of the multipliers that you can use to determine the amps per horsepower and so on. In the case where Marvin was at, they had a 100 horsepower motor. The motor was running extremely hot when he touches it. I asked him to calculate the fan speed, and the fan speed was 2070. At this point, I asked him how many amps was the motor rated for. He came back, texted me as we're going back and forth, and told me that the nameplate was 112 amp. Then I asked him to go find out what the motor actually was running at. So he came back and the motor current was 150 amps. So if we take 150 amps and we divide it, which I'm going to show you part of this formula just to start with, for a 460 volt motor, use the multiplier 1.25 into 150, and you'll get the horsepower that that fan was trying to make with the motor that was 100 horse. So if we take a 100 horsepower times 1.25, we're pulling 125 amps. That's just a quick way of doing this. His motor was really rated at 112 amps full load, not 125. Okay, just so you know. Now, the idea is that if we took the same nameplate, so we've got 460 volt with 112 amps. So if we took 100 horsepower divided by 112, we come up with 1.12 amps per horsepower. So now if we take the 150 amps that we were pulling divided by 1.12 for every amp per horse, the motor required would have been 134 horsepower. Okay, well, you're not going to find that. The only way you're going to get there is to put 150 horse in its place. So that's just to give you an idea that we were almost 50 horsepower shy of being able to make this thing run and last. The other thing here is that by changing these pulleys, we didn't know this had happened. The customer did it and didn't tell us. So we get there thinking this thing's always been running at 2070 and the motor's always been there, and all we're going to try to do is balance the fan. Well, here's another issue. By taking it from 1775 up to 2070, we may have been running on a critical, meaning that the vibration now from the fan is a resonance issue or a problem where you're not going to be able to balance it. You can't be within 10% either direction of a critical. So one thought is to actually take the vibration meter and see if you've got any harmonics that are equal coming down. So if you've got 2,000 RPM and you all of a sudden start shaking at 1,000 coming down and then 0 all the way down, you can sit there and say every 1,000 is going to be a critical point. So 2,000 would be right on a critical. So it wouldn't run. So there's more to it than just trying to figure out, how to balance it. By getting there, he was able to go back and tell him, you got the wrong motor. You may be running at a higher speed now that's causing part of the vibration problem, and go from there. So the main thing I wanted to do, though, is to get it across to everybody so they understand that when you're operating with pulleys and changing pulley diameters, and a customer doesn't have one that's the right size, what's going to happen? So I'm going to go ahead and start again right now at the top of this up here. And basically, we're looking at a 125 horsepower machine, 1775 RPM. Our full load current is 156 amps, and we're running on 460 volts. This is important so that you can do the equations that I'm going to ask you to do in the next couple of lines here. Our motor pulley is 10.5 inches. Our fan pulley is 9 inches. So right now what we want to do is divide these two. So if you would take your calculators or your phones, however you want to do it, and divide these two, you should get this number. As soon as you get that number, if we times it by the original RPM, it will now tell us what our new speed is going to be at the fan. Okay? So now you know that our fan speed is 2070. These are the answers down here in this section that I'm going to try to show you. So our new fan is 2070. All right, so the next thing we want to do is calculate what our horsepower is going to have happen, because we now jumped up to 2070 RPM. So our horsepower is this formula. We're going to take the new RPM divided by the original RPM, which is 1775. Our new RPM is 2070. We're going to come up with the 1.166 number. This small v upward with the 3 is to the power 3, which just means that you're going to take your 1.666 times 1.666 times 1.66 and you will get this number right here, 1.586. I'm showing this because it's a whole number. It's easy for you to remember. All you're doing is 2 times 2 times 2 equals 8. Okay? So that just gives you an idea how. If you have a calculator with this on it, it makes it real easy to do. It's on your phones as X3. So if you plug in the number 1.666 times X3, or not times X3, just X3, it'll give you the 1.586 number. Okay? And these numbers are close to being rounded off, so if you're point here or there, do not worry about it. It's not a big deal. Okay? Once we've got that number, we're going to times it by our original 125 horsepower up here. The new horsepower required to go that additional speed from 1775 to 2070 is 198 horsepower now. So you're going to have a 200 horsepower motor in there to do the job that was 125 horsepower because you increased the speed. Marvin, how much is that? 1775 minus 2070. So additional 295 RPM, is that right?
Yes.
I just want to double check that so I'm sure. And you're correct, okay. So for 300 RPM more, we needed 75 horsepower more to get there, okay. And a lot of people don't know that. So they just start switching pulleys thinking that they can go whatever speed they want. I'm going to throw a story out to you that's fairly quick. And if we do the formula, you're going to start to see some of this. We have a farmer that came in and bought a 50 horsepower motor at 3,600 RPM. 2 days later, he came back and bought another one. A couple of days later, he came back and bought a third one. The problem was, by doing this, I finally asked him, I said, "You got a lot of these, huh?" And he said, "No, I only got one." What he was doing was he didn't tell me that he had a 50 horse at 1,800 RPM. So he took his 1,800 RPM motor off, he put his 50 horse 3,600 RPM motor, and it would take less than a day to fry him. Okay? He never knew anything about checking amp probes or anything else, no electrical part of it. He just stuck them in and wired it in and turned them on. Okay? So if you calculate 3,600 divided by 1,800, just like here, take your number, so I'll do it with you. So 3,600 divided by 1,800 is 2. Then we're going to raise it to the third power, which now makes it 8, times the 50 horsepower in this case. What'd you get? 400. It now required a 400 horsepower motor in the place that he had a 50 horsepower to get it to not burn up and to do the job he was looking for. So he would have needed a 400 horsepower, 3,600 RPM motor to replace his 50 horsepower, 1,800 RPM motor. Besides buying new contactors and new wire and everything else that came with that package. Okay, so it kind of gives you a little bit of an idea of why I'm talking about some of this, so that everybody's geared up to realize 2 pulleys the same size is 1 to 1. So if we're sitting there 1 to 1 and you're looking at them, you can pretty much bet whatever your motor speed is, the fan's running at. But once you start changing that pulley on the fan, everything's going to change. If we're going down in speed, you have no problem. It's when you go from the nameplate above is when everything starts to go to hell. Okay? So, before we get into this part here, I want you to understand again, this is in our handbook, and basically what it says in the electrical handbook is that anything 200 horsepower and above is 0.2 on 460 volt. I've made this simple, so it's at 230, it's 2.5. If we double the voltage, it's half of that. So now it's 1.25. 1.25 and 1.25 is 2.5. Okay? 2300, if we take the 0 off the end, you're back to 230. We move the decimal place in front of it, and it's now 0.25. 4160, we're going to use 0.125 instead of 1.25. So you can remember this in your head. And the reason I'm saying that is you're going to have to tell me the answers here for this question. And it's not hard as long as you can look at the sheet that I've handed out to everybody up there in LA as well as here and start looking at changing the pulley sizes, changing speed formula, so you can go from there. So one of the first things we know, it's a 300 horsepower in this question. We know it's 4160 because we're being told it is. We're also 1775 RPM. Okay? We know our motor pulley. We know our fan pulley. The questions I have here is that we want to increase the fan to 2200 RPM. Now we want to know what new pulley size we're going to need to get to that speed. Okay? And what you can do is, if you draw a line straight across here and divide these two, you're going to come up with the original RPM. Okay? The motor was at 1775, but this particular motor was running with these pulleys. So I want the same motor to run, but I want to get to this RPM now. So let's see if you guys can figure out how to calculate the speed as close as you can. They will not be whole numbers. Normally pulleys are going to be even numbered, like 6 inch, 7 inch. I don't buy enough pulleys to know if they come in 1/4 inch or 1/2 inch increments in diameters, where you could really fine tune a RPM if you were trying to only do it with our pulleys. The best scenario for something like this is to go 1-to-1 and put a VFD on it. Now you can adjust the VFD and watch the motor current and be in the perfect world for everything to work. But if you don't have the VFD and you're trying to increase speed, this is the way of getting there, as long as you calculate it right, so you're not burning up your motor. Okay? So once again, if this was me, I would be taking that number and calculating into this number what it's going to take to get me to here, to 2200, or as close as I can. So you guys take a few minutes here and see what you can come up with. And once we know this new speed, then we can calculate the new fan speed, which should be that. And then our new horsepower required to get there, and then our new full load amps. We don't have our amps up here, but we have a question that says, what's our full load amp?
If you want to let us know when you're done with the calculations, you can just text to 775-433-9390 so that we know when you're done and we can go over those answers.
Another thing I would like to talk about is on your second sheet, I added this to it so that you can use the formulas easier down the road or whatever. This is right out of the ESA mechanical handbook. So it is actually, it's actually very good to know it and understand it, because you could sit there and try to figure this stuff out. I used it not too long ago with a fan that we had here in the shop when Marvin and Keaton here were trying to balance this fan. I was trying to see if we were, what speeds we were running, and if we were in a critical on it, same thing. So it kind of gives you a good idea of where you're at. And again, we're going to look at motor current, motor current, motor current. That's what's going to burn up here if we got the motor current above what it's rated for. And this way we get a chance to see what we've got.
Would the same principle for increased horsepower apply if you're overspeeding a motor by a VFD?
Yes.
Overspeeding a fan with a VFD?
Yes. That's why I was saying earlier that the VFD would be the right way to go, but most people don't have VFDs because it costs too much money or blah, blah, whatever the reason be. So grabbing a pulley over here and grabbing a pulley over there for whatever money, sticking it on gets them basically to the speeds they want to go. The sad part is they don't understand this kind of stuff that we're talking about, and they get themselves into trouble by going over current. Slowing it down, no problem. But most people don't slow the machines down. They want more production. They want to go faster. They need more airflow, or they're pushing diatomaceous earth or something with their fan blades, and they want to push more product through it. So in most cases, it's going up, not down.
If you are going slower and you don't need to go fast, you would want the lower horsepower, right, for efficiency purposes?
Yes, and that would be the part about sizing the motor properly for the application. So if we're going to go from 100 horsepower, now we're at 75, we're only using the 75. If it's a small change, it's not as big because their no load amperage for each motor are pretty much the same. But I'll give you an example of another story is a 350 horsepower in, and told me there was no hurry getting it rewound or anything else because they have a 450 they're going to put in its place until the rewind's done. Well, about 3 days later, I started getting phone calls every day looking for the motor to come back because they finally found out that the 450 was pulling as much amperage, or more, I should say, than the 350 was no load. So they're selling power, so they were losing kW to sell because that motor was costing them more to run than the 350 was. So that gives you another idea of just sizing the motor properly for the right horsepower or application, let's use the word.
So we haven't had any questions yet, but we did have somebody text that, I failed math class, right? Which is okay because there's people that can help you. The main point of this is making sure, and you can double check your answers with other people, but making sure you're thinking about these things when you're in the field so that we don't solve one problem and leave the other problem out there, and it ends up burning up a motor we repaired, and then they want to hold us accountable for that. Plus, the more you can solve at your customer's site, whether it has to do with us or not, you point out other problems that they can fix and they're able to run more efficiently, you're adding value for them to use us rather than the competitor.
Damn right. We get them out of trouble and they instantly going to keep thinking about us when they have problems, at least. This would be really, in my opinion, important for the guys that are doing field service work. The big thing is that if you're thinking before you go out, like Dan said, you're going to go right over to the job. You're going to find the motor that you're looking for and see what its amperage is, why it's running. And see if you're in the game. Are you above or below? If you're below, continue on with the process. If you're above, try to figure out what's going on now. Big thing is I'm sorry, go ahead.
Does the same cube formula apply for pumps as well as fans?
Yep. So it applies to fans and pumps or variable torque. Okay, and variable torque's the big keyword. And I seriously believe that once you understand this better, you're going to start going, oh my God, the cooler motor over there's got the motor running hot and it's pulling higher amperage, but it was the same horsepower and all we did was change the pulley.
Can you go over the cubed part of your formula one more time?
Yeah, so let's just use the real number that's here. So this number, 1.166. So we're going to times it by itself, 1.166. So if we take the calculator and we go 1.166 times 1.166, that equals
No,
time.
Yeah. But these two numbers times equals that. Then times that number again by 1.166 gives me the answer. So what I was saying is 1.166 times 1.166 equals 1.359 times 1.166 equals 1.585. So all we're doing is we're timesing that number by itself here, and then that number times itself here. And that comes out to this 1.588, which is the number right here. Whether you round it up or not, I told you don't worry about the 586 or 585 for this. Then we're going to times the horsepower to get the new horsepower that we've changed this RPMs for. So in this case, like I was just saying, when we're talking about the 125 horsepower motor, we've got to do an additional 50 horsepower to be able to keep it from burning out. And then we've calculated that new amperage again. So when we get over here, and one of them says, what's the new full load? Once you have calculated the new horsepower, you'll take your new horsepower times the multiplier that is asked for in the equation.
I noticed after doing the calculations on here myself, then looking back at yours, we have different pulley sizes only because I kept one consistent. So you could have multiple different pulley sizes.
You could change either side.
Yeah.
In this case, it was easier for what I was checking to change one.
Right. Yeah. And that's what I did. I just changed one. I just changed the other one. I have a question that came in. It says also measure when you're measuring a pulley to figure out the diameter. Do you measure in the grooves or outside of the grooves? One thing real quick before we go to Jim, just used to sell a lot of pulleys and sheaves. Pulleys are technically for flat belts. Sheaves are the ones that actually have the grooves, but I'll give the question back to Jim.
Measure the outside diameter. Okay. The when we're looking at these equations, they're going to tell you right here, motor pulley diameter. So just take the diameter. You don't have to worry about at the bottom of the V or at the top. Just measure straight across top to top to use for your formula. If you're in the field and you're doing this, you can check it with it shut down and then go use your analyzer if you have it or know how to use it and see what the actual RPM is by tacking it. So it could be tacked, okay? And it'll verify what you pretty much calculated. This really seems to be a little confusing when you first start it, but once you start doing the equation more and more and more, you know, right on the red portion of these up here is the formula for new horsepower, changing the pulley size to change the speed, when driving the fan or a pump at a lower speed, pretty much giving you the equations right there to use. Just put in your numbers for the pulleys, which are 17.5, where we're asking for 10.5 in this part, or I'm actually showing you 10.5. So the formula is right there in front of you, so you can make it easier.
I know Jim seems to be able to remember everything, but I personally just make sure I can remember where I put things. So any of this stuff, you have it now. So whether you can figure it out real quick or not, or if it comes off the top of your head, at least you know how to get there now. You've got the formulas, you got everything you need now, so you can always look back at it as well.
I hope the point of this is that when you go out to a site, or even if it's in the shop, let's just say you got to go change something on the lathe and you want to make it go faster or go slower or something, at least you know. Jim said someplace there's a formula that does this. You know, you can always call me and say, I got these two, what's your calculation? I want to compare it to mine. I don't care. It's no big deal. The idea is that you've got some idea in your mind that I can change pulleys very safely going down in speed. I cannot when I go up in speed within reason. So if I looked at my motor and said that I had 100 horsepower and it was a 1.15 service factor, I really have 115 horse to work with if I run it in the service factor 100%. So I could use the 115 number to do a lot of these calculations with. My motor's going to run hotter because I'm pushing it to the top of the ceiling when I do that. I've now increased the amperage to the full service factor capacity. So as things start to warm up in the shop down in LA, let's say, and it's 105 degrees, you're going to have motors running really, really hot down there. Okay? So, you know, putting them into the top of the service factor is not a great idea unless you have no other choices. The right idea would be to change the motor to the proper horsepower size that you calculated. And now you've got some chance to have it just keep on running all the time and not be such an issue. Remember about the balancing part of it. If you're going out on a balancing job, or you're trying to find out, this thing never shook before, why is it now? Start asking, has anybody changed any pulleys recently? Yeah, we had one that was bad, we changed it. Was it the same size? Was there something that's changed here? You know, because now you can calculate it. Another thing is most of your plants that are big plants, like cement plants or mines or power plants, these guys seem to always have ways of recording and keeping a recording of what has been running like. So you could go back and ask, do you have any trend on this motor showing the motor current? So here it is, it's been 75 amps all this time, and then last month for some reason it jumped up to 125. Well, what did we do last month? Did we do some maintenance on it? Did they change the pulleys and so on? Okay. Another one would be is if they put a different motor on it and we went up in RPMs. Naturally, that's a problem if you went from 18 to 36, but let's say that it was originally a 1725 and it went up to 1785. So there's a change. So now the horsepower is going to go up, and we would now have to look at the current for it. VFDs are actually, the VFDs is the way to go, because now, like I said, I can sit there and monitor the motor current, and I can tack the fan, and I can sit there and see when I'm driving this VFD at what point my ceiling is for the amperage for the motor, and say, okay, that's it, stop, don't go any further. We can't, you know, we keep it right there. So knowing the, you know, that the motor can operate at this much temperature, like a Class F motor, and I'm running it, I could pretty much run a motor and overspeed it and kind of watch the currents and the temperature and probably be pretty safe running it. If I wasn't monitoring bearing temps or winding temps, it'd be a crapshoot. But I do know that I can run a bearing pretty, you know, 180 degrees without any issues. I don't like it, but I could go that high. It's going to fail anytime after 200, pretty much, 220, and you're on borrowed time. And the windings are good for a Class F up to 311 Fahrenheit. So if I'm running 250, it's not going to scare me at all, as far as that goes. So we can sit there and play with our VFD, driving this motor and monitoring temperatures as well, and still keep that motor from dying as if we know what we're doing. Okay. So I'm actually hoping by the time this is done, you're going to look at things a little different and just say that we're changing speeds and we're getting what we want, but we have to be really careful not to burn up our motor in the process. It's not as easy as just say, yeah, let's make the fan go 3,600. Unless you're driving a 400 horse that used to be a 50.
It doesn't look like we have any more questions for today, so thanks again. And boys and girls and non-binaries, come back next week for Jim Hudspeth's Neighborhood.